Welcome back. This video is going to cover non-seasonal ARIMA models. This is the fourth video on our chapter covering ARIMA models, so if you haven't already watched the previous three videos, you should do so before watching this one, otherwise this video is not going to make a lot of sense. We covered autoregressive moving average models, or ARMA models, and what I told you was ARMA models assume stationarity, so you can only use them if the data are stationary. Well, what do you do if you have non-stationary data? If you go back to the first video this week, we talked about differencing, and I showed that differencing is a very good way to turn a non-stationary process into a stationary one. So we covered both seasonal and first-order differencing. The basic idea of ARIMA is that we're going to add a differencing step before fitting an ARMA model. Before we get into that, I'd like to define a new term, although this is really just another name for something we covered before. Before we talked about random walks with drifts, we're now going to call that an integrated process. This is the random walk with drift. It just says that my current observation is just some drift constant plus where I was and then some random error. We're going to now add this integrated process. So instead of just having an autoregressive moving average process, we're going to have an autoregressive integrated moving average process where we add this differencing step before doing the ARMA model. The second parameter in this notation is going to indicate the number of differences that we take. So for example, if I want to fit an ARIMA P1Q model, what that means is take one difference and then go fit an ARMA PQ. Likewise, an ARIMA 2Q model would take second order differences and then fit an ARMA model. In general, you could take up to D differences, although pretty uncommon to ever go above one difference. I mentioned earlier that if you have a quadratic trend, you would need second order differences. Hopefully we've already gotten this down to a linear trend with some sort of Box-Cox transformation, and therefore we would only need one difference. How do we fit these models in R? Well, as I mentioned to you in the previous video, there's an ARIMA function. You want to use the ARIMA function with a capital A. There's also an ARIMA function with a little a. The one with a big A is basically a wrapper for the one with a little a, but it has some different options that are very useful to us. It's a little bit more user-friendly than the little a one. If you ever want to simulate data from an ARIMA model, it's not bad for you to write your own function, but R actually has a function built in to simulate data from ARIMA models called arima.sim. Now let's talk about a few special ARIMA models. The first one that I want to talk about is the ARIMA 111 model. We're going to take one difference. We'll have one autoregressive coefficient and one moving average coefficient. Let's go write this out. This is the number of differences, which we call D. So this is saying y prime sub t is equal to, now this term is the number of autoregressive coefficients that we want to include. If we have a drift constant, it's going to be c plus phi times y t minus 1 prime. This third term is the number of moving average terms that we want in our model. So this is saying include 1. So we're going to have epsilon t plus theta epsilon t minus 1. This term comes from there. This term is saying we need this piece, and then the differencing is saying you need the primes there. This is really yt minus yt minus 1. So that's the difference at time t is equal to c plus phi times yt minus 1 minus yt minus 2. Then we have epsilon t plus theta epsilon t minus 1. We can also write this in backshift notation. So with backshift notation, remember that we put all of our y's on one side and we put all of the epsilons and the constants over on the other side. The way we would do this in backshift notation is we would take 1 minus b gives us the difference, and then 1 minus phi b gives us the AR1 term. And all of this is applied to yt. On the right-hand side, we have c plus 1 plus theta b times epsilon t. What's always a good idea, confirm this. So we can multiply this out, just 1 minus b minus phi b plus phi b squared, all applied to yt. On the right-hand side, we have c plus, well, might as well write this out, epsilon sub t plus theta epsilon t minus 1, where when I take b times epsilon t, that gives me epsilon t minus 1. Let's go distribute yt across all of this. So this is yt. This is going to be minus yt minus 1. Then we have a negative phi yt minus 1. And this is going to be plus phi yt minus 2. And that's equal to the same thing that we had before. Now, hopefully you'll recognize what I have here is identical to what I did at the top. So this is equal to that. A few more things to note. This constant, by default, is not included in the model unless you specifically ask for it. So the way you ask for it is you say include.drift equals true, and that gets you the constant. There are a lot of other models that we've met that are special cases of the ARIMA model. If we have an ARIMA model with 0, 0, 0 as the parameters, that just gives us white noise. If you're not convinced of that, an ARIMA 0, 0, 0 model means no differences, so we don't take any differences. And then this is equal to C, and I have 0 autoregressive terms. I have 0 moving average terms. All I have is the error, and so we're left with white noise. So we recognize that as a white noise process. If we take an ARIMA 0, 1, 0 model, we get the random walk, and if we include the drift C term, we get the random walk with a drift. That is exactly what I showed here. Likewise, the autoregressive models that we talked about are special cases of ARIMA. The moving average models are all special cases. And it turns out a lot of exponential smoothing models can be written as ARIMA models. So you can click on this link and be brought to a website that explains a lot of these. I'm not going to take us through the math on that. How do we build an ARIMA model? The textbook that we're using has a really good flowchart, and so we're going to be following this flowchart. The very first thing that we'll do is we should always plot our data, look for unusual observations, try to understand if we see some seasonal patterns, use all of those diagnostics that we covered back in the first week of class. So remember, we had some additional plots that would help us diagnose if there were seasonal patterns. So it's a good idea to look at all of those. The next step is we're going to use a Box-Cox transformation to stabilize the variance. This could also be used to turn exponential trends into linear trends. So remember that if you have an exponential trend and you log it, all of a sudden you have a linear trend in the log data. So we'll be taking some Box-Cox transformations as the second step. The third step is to either use an automated algorithm for choosing an ARIMA model. This algorithm is very similar to the stepwise regression algorithm that you learned back in the regression class. Alternatively, you might want to build a model by yourself. If you choose to go down this left route, the first thing that you're going to do is select the number of differences. So we will take a difference if we see non-stationary data. Then we'll use the unit root tests, such as the KPSS test that we studied earlier, to see if we've gotten it down to stationarity. If it's not stationary, then we'll take a second difference, apply the KPSS test again. Having differenced the data to the point where it's stationary, the next step is to look at the ACF and the partial ACF plots. This is going to help us figure out how many autoregressive and moving average terms we're going to need. So remember, if we have an ACF plot that declines geometrically with the number of lags, that's a signal that we need some sort of autoregressive terms in our model. If we look at the partial autocorrelation plot and only the first one is significant, that's a signal we need an autoregressive model of order 1. Having looked at these plots, that's going to give us some sense of what we should choose for P and Q. So we choose D back in step 3, the differences. We choose our lambda in step 2. This is where we're figuring out what sorts of P and Q values we want in our model. Having done that, we'll go fit a couple models and then we'll compare them with some penalized measure of fit. Our author prefers the corrected AIC, and we're going to be using that in this class as well. Once we choose our favorite model, then what we're going to do, just as we did with regression, is examine the residuals. What we'd like to see in these residuals is, I called it the snowstorm back in regression, and by snowstorm I mean no pattern whatsoever. So if there are any patterns in the residuals, if there's autocorrelations between them, what that means is you haven't modeled all the structure in the data. So there's more stuff to find, and you would need to come back, add some more terms to the model. Once we've identified a good model, then we can go compute our forecasts. I'd like to illustrate this procedure on a real data set, but before I do that, I want to talk a little bit about this right path. What is this stepwise algorithm? The way stepwise works is it's going to go find differences automatically. It'll do a KPSS test on the raw data. If it finds it's non-stationary, it will take a difference. KPSS test again. If it finds that it's still non-stationary, it will do a second difference. At this point, we will have found our parameter D. Next, it moves on to finding P and Q. So the way it does this is it tries these 4 models and uses the smallest AIC C value to be what I'm going to call the current model. So the best of these will give this kind of starting current model. Step 3 says we're going to take this current model and try to vary it. So we're going to add and subtract 1 from the P and Q value. We also might try to include a drift term in the model, and we're going to keep doing this until no further improvement can be realized. Having done that, we return the model. Let's go back to the Shampoo data set that we analyzed when we covered the Holt exponential smoothing method. We are given the sales for some shampoo brand 3 years. The reason I used this data set with the Holt method is because there is not strong seasonality. So shampoo is just a category where we don't see a lot of variation across seasons. It's not like people wash their hair more often in summer than they do in winter. If we were to analyze a category like beer or ice cream, there would be strong seasonal effects, and we would need a model that would capture the seasonality. So either we'd use a Holt Winters model or a seasonal ARIMA model, which we'll cover in my next video. That's why I'm using this Shampoo data set. The first step in this process from Heinemann is to look at the data. So let's go do that. We've already done this back last week, and what we see is something that may be in exponential growth. Looks a little bit like exponential growth to me. I don't see any terrible heteroscedasticity in the data, but I do see a geometric trend. Let's go to step 2. So step 2 is to see if we need a Box-Cox transformation. And what we see is that the automatic Box-Cox procedure wants to choose a value around 0.27. Remember that if this were 0, that would be a log function, while if it were 1, that would mean no transformation. This function is saying we're probably better off taking a transformation, and that's exactly what we did back when we covered Holt's method. I'm going to create a transformed version of this. Now, all of the modeling functions, ARIMA and Holt, will do the transformation for us, but I'm going to create a transformed version. And if we go look at our autoplot, what we see is that the exponential trend has been removed. Now I see more of a linear trend. Well, let's go back to our flowchart. The next step is to compute differences if necessary. Clearly this is non-stationary. I'm going to try some first-order differences. If I take my first-order differences, what we see is something that looks pretty stationary. So I think differencing has fixed our problem. Now I'll go do a KPSS test, and what we see is that our test statistic is pretty tiny. It's less than the critical value for using a significance level of 10%. It's way less than the 5%, 2.5%, any of those cutoffs. So basically, we cannot reject the null hypothesis of stationarity. We also studied the adjusted Dickey-Fuller test, so let's go use that. Remember that the null hypothesis is non-stationarity, the alternative is stationarity, the p-value is tiny, so we reject the null hypothesis and go with stationarity. So I think the differencing has solved our problem. So we have just done step 3. Well, let's go on to step 4 and examine our ACF and PACF plots. The way I like to do this is with the TS display command. And when we look at this, we get something kind of unusual. The first autocorrelation is very big and negative. I think what's happening here could have to do with forward buying. So forward buying is where you put your shampoo on sale. Maybe I walk home with 2 bottles of shampoo. I don't use that much shampoo, and therefore, now that I've got 2 bottles of shampoo in the pantry, I don't need to buy shampoo next month. The fact that you put it on sale and I load it up means that next month, I'm not going to be buying as much shampoo. That would explain why we have this negative autocorrelation. When I look at the PACF, I've got this first significant big PACF. Everything else is not significant. I'm thinking maybe some sort of autoregressive model might do the trick for me. We're going to go try that. So I'm going to try AR1. I'm also going to try an ARIMA 1-1 model. And so what I'm trying to get across is I'm going to try some plausible models here in 5 based on what I saw back in step 4. So to fit an ARIMA 1-1 model, this is what we get. Notice my coefficient is 0.69. So let's go write out what this model looks like. My model would be something like this. This is the AR1 model. Y prime t is equal to, notice there is no drift constant in this model. So it was minus 0.69 times y prime t minus 1. And then, of course, there's going to be some errors, but no moving average term, so it's just white noise that we're adding. What we're saying is if our sales have gone up in period t, that is inversely related to the change in my sales in the previous period. Now, of course, we could fill in all the pieces here and write out the equation without differencing. So this would be minus 0.69 times y t minus 1 minus y t minus 2 plus our epsilons. And then we could go move this term over to the other side if we want. This would be yt is equal to, we could write this as 1 minus 0.69 times y t minus 1 and then we have two minuses that combine to a plus 0.69 times y t minus 2, and then we have our errors. So our predicted value at time period t is really just an average between the most recent value and the previous value. So we're giving a little more weight to the previous value. Well, let's go fit the ARIMA 1.1 model with differencing. So notice we don't have a drift constant. The estimated equation is going to be y prime sub t. So the change in sales at time t is equal to minus 0.53 times the change in sales at time t minus 1 minus 0.34 times epsilon t minus 1 plus epsilon t. Step 5 says to use AIC corrected to see which model is better. So let's go take a look at our corrected AICs. The ARIMA model has a value of 118, while the autoregressive model is 116.9. Remember, we want small AIC, and so the autoregressive model is a little bit better than the ARIMA model, but not by much. Let's move on to step 6, which is to check our residuals. And when I look at these residuals, I'm looking for a couple things. Number one, I don't want any big autocorrelations between them. None of my autocorrelations are significant. I'd like to have a normal distribution of these errors since I've assumed them. That's not really in question here. And I don't want to see any patterns in the time plot. So this is all looking very good. We can use the Young box test. The p-value is very large, suggesting I can't reject the null hypothesis that the first 7 autocorrelations are all equal to 0. Basically, what I would conclude is model 1 is pretty good. If I do the same for model 2, none of my ACF values are significant. Values are normal. The Young box test is even more non-significant. And so either of these models would be good models. Since AIC is a little bit lower, I'd prefer to use the AR model versus the ARIMA model, but both are defensible. Let's go down the other path. So remember, the other path is we hand it off to Autoarima and see what it finds. Autoarima takes us to a very different place. It says we don't need any autoregressive terms, but we need 2 moving average terms. Let's go write out this model. So I wrote those 3 coefficients here. This will be my model. So my difference data at time t is the drift coefficient. Now we don't have any autoregressive terms, so I don't need to write in any fees. This is going to be what I write times epsilon t minus 1. This is times epsilon t minus 2. And I really have an epsilon t in there. So that is the model that has been generating my data. Now, we could get rid of the differencing. So just note that this is yt minus 1. So we could write this as yt is equal to the previous y value. Then we're going to take a jump of size 0.18. So we always go up by 0.18. But then we're going to adjust based on the errors. And so I'll just finish writing this out. If we really want to finish specifying the model, the variance of these epsilons is 1.20, call it. Epsilon t is distributed normally, independently distributed, 0, 1.20. Well, let's go look at our residual plot and see what we have. None of my autocorrelations are significant. The residuals are pretty normal. I see something that looks, I see a little bit of heteroscedasticity in these residuals. My Young box test is not significant. I'd now like to compare this with the best Holt model that we came up with. I'm going to set the number of periods to forecast into the future to equal 12. Let's go use the damped trend, which we found to be the best model. If I look at the residuals from this model, none of the ACFs are significant. I have something that looks like random noise. So that's a pretty good model. Now I'm going to make myself a plot that compares all of these fits. What we see is really interesting because the ARIMA model with the drift term and the Holt method do very well. In fact, the fits are almost on top of each other. The ARIMA models without the drift term don't do very well. So it's very important to have that drift term in your model. Another way we could test this is to have a test and training set. So unfortunately, this time series only has 3 years of data. I'll use the first 2 years as a training set. That'll give me 24 cases to estimate my coefficients. And then we'll use the last 12 cases as a test set. I've now defined an object train that has those first 2 years. Let's go estimate an ARIMA model using only the training data. We're going to give it a drift constant, and this time I'm only going to give it an autoregressive term. I'm not going to give it the moving average. This is the AR1 model, but I'm going to improve on it slightly by including a drift constant. We'll also let Autoarima do its thing, and you'll see now Autoarima chooses a slightly different model. It actually fits the same one. I'll compare that with 2 different Holt models. So one with the damp trend, one without the damp trend. We can use the accuracy function to compare the measures on the test set. Here we have our measures for the drift model, for the one without drift. What we see is that on the training set, both models do pretty well, but on the test set, the one with the drift terms do much better, as we saw from the plot. If we go to our Holt models, what we see is they do a little bit better on the training set than the ARIMA models, and I would say that the damped Holt model does much better than any of the other models. So in this particular case, I would say the damped Holt model wins. We can make a comparison of all these models if I generate a plot. So when we look at the plot, it becomes clear why the damped Holt did so much better, because it's clearly passing through almost the middle of the scatter plot, whereas the other 2 models, the ARIMA model and the Holt model, they get some trend, but they're systematically below the point. Of course, the basic or autoregressive model, so the ARIMA 110, so the autoregressive model with a difference, does very poorly. I'd like to talk about one more issue with ARIMA models, which is how do we do forecasting? We're going to solve the equation for y. Then we're going to compute forecasts recursively. So we're going to start with the next period, then the period after that, then 3 periods out, all the way through however many periods we wish to go. In our equation for yt, we're going to use a yt if we've observed it. So that's going to be the case whenever a yt is less than or equal to the end of the data. Otherwise, we plug in the forecast. So I'm going to use blue font to indicate anything that was a forecast value, black font for anything that's observed. When it comes to the errors, we will plug in the estimated error if it's known. Otherwise, we're going to plug in the mean, which is 0. So let's go look at the ARIMA 1.1 model. So if we write the ARIMA 1.1 model in terms of t, this is what we get. There might be a drift term. This is your autoregressive term. This is the moving average term. Let's go compute the forecast value for 1 period into the future. So this would be big T plus 1. And we're only allowed to use the information available in the first big T observations. So in order to do this, we'll just take our estimated drift term, we'll take our estimated autoregressive term times the observed y big T value. Then we're going to take the estimated moving average term times whatever we computed our y hat sub t to be. If we want to go 2 periods into the future, what we're going to do is take our estimated drift term. Now we're going to plug in whatever we computed in the previous step. And then we have, so we don't know what the error is at time t plus 2, and we don't know what the error is at time t plus 1, so we just drop in their means. So this would be the general equation for making a forecast h periods into the future. For an ARIMA 111 model, we have to worry about the differencing. So here's a statement of the ARIMA 111 model without any drift constant. I'm going to replace the differenced yt with what that difference means. So yt minus 1. I'll do the exact same thing for the differenced yt minus 1 value. Now I'm going to move yt minus 1 over to the other side, collect my terms, and this is my equation. So having solved for yt, let's go look at what the equations would be for h equal to 1, 2, 3, and so forth. So if we want to forecast the value 1 period into the future, we will be using the observed value of y big T. So that's the previous period, and we've actually observed that. Likewise, we've observed the value for 2 periods back. We also have the error 1 period back. So if we're 1 period into the future, the error 1 period back would epsilon hat sub t. What if we want to go 2 periods in the future? Well, we haven't observed what happened in the previous period, so we're going to plug in the forecast value that we computed previously. We have observed what happened 2 periods back, which is y sub big T, so we can just drop in that observed value. What if we go 3 periods out? Well, now we haven't observed what happened in the previous period or the period before that, so we put in the forecasts, and that's what we would do for all future periods when making forecasts. It's always a good idea to make sure that you understand what the software is doing. I worked out the forecast equations for the 3 models that we used in the Shampoo data set. Then what I did is I wrote some R code just to confirm that my forecasts that I computed by hand equaled the ones using the forecast function in R. So I encourage you to look at this and try it on your own, and I think you'll have a better understanding of how these forecasts are made.